This plane was canceled. Canceled, dead, buried. The President of the United States signed the papers and said, it's over.
And 4 years later, they resurrected it. Why? Because it turned out that without it,
there was a gap in the American arsenal that no other plane could fill. It's called the B-1B Lancer. It's not the stealthiest, it's not the most modern, it's not the most expensive, but it can carry more weapons than just about anything else that flies. Faster, farther, for longer.
And today you're going to see how something like this is made.
This stress point won't hold at Mach 2. Rub the numbers again on the rule. Verify the shear strength.
To understand how the B-1B was built, you first have to understand why it almost didn't exist. It all started in the 1960s. The Pentagon had a serious problem. The B-52 could no longer penetrate Soviet airspace. Radar had improved. Missiles had improved. A huge plane flying high and slow was basically an easy target. The solution they proposed was radical, a bomber that flew at very low altitude, very low, very fast, and reached its target before the radar could properly detect it. Rockwell won the contract in 1970. They began building the B-1A, an aircraft designed for Mach 2, brutal on paper, and in 1977, canceled. Jimmy Carter signed the cancellation. Cruise missiles were cheaper, they said. The B-1 was too expensive, they said. 4 years of work, 4 prototypes, down the drain. But this is where the story gets interesting. When Reagan came to power in 1981, he relaunched the program. But he didn't relaunch the same aircraft. He relaunched a different one, smarter, more useful, the B-1B. Lower top speed than the B-1A, but more payload, more range, better for flying low and fast in real-world combat conditions. What do you gain by changing the design like this? An aircraft that can carry 34 tons of ordnance, 34. And the advantage that provides is simple. No other bomber in the arsenal can do the same. That's what you're going to see manufactured now. The B-1B's fuselage is one of the most brutal engineering challenges in modern aviation. Why? Because this aircraft has to do 3 things that don't normally coexist: fly very fast, fly very low in brutal turbulence, and carry an absurd amount of weaponry inside. That means the structure has to withstand loads that most aircraft never experience. Every time the B-1B flies at low altitude under real-world conditions, the fuselage is hit by turbulence that would be fatal to a conventional airframe. What happens at this stage? Structural sections are built from high-strength titanium and aluminum, assembled to military tolerances. 3 internal weapons bays are designed inside that long airframe, something that greatly complicates the structure because rigidity must be maintained with enormous cavities inside. Why does it matter so much? Because internal payload capacity is what sets the B-1B apart. An aircraft that carries its weapons externally has a huge radar signature and aerodynamic drag that limits its speed. The B-1B packs everything in. What do you get? A platform that, despite its size, can fly at over Mach 1.2 at low altitude. And the tactical advantage of that is that the enemy's reaction time is reduced to seconds. See how this is built.
Check the laser track on Sector 4.
Reading within tolerance.
Good. Proceed with the final sequence.
Is that line secured yet?
Almost. Just need to tighten this connection.
All right, I'm moving forward with the harness.
Slow down, bring it down 5 inches.
Got it.
Got it. And hold. Slow down, slow down. Copy that, slowing down.
Watch the starboard side.
Steady, hold it right there.
We need to verify the wiring harness routing right here before they close that panel.
Okay, let's double check the diagram for the aft bay.
Check the angle on the left side. Reading 92 degrees. It's within tolerance. Here we see the crucial variable geometry mechanism. The tolerances on these actuators are measured.
This aircraft changes shape in midair. That's not a metaphor. It's literal. The B-1B's wings move. For takeoff and landing, they open, like this, to generate more lift at low speeds. For high-speed flight, they sweep back, like this, to reduce drag and gain speed. Why build something so complex? Because if you design a fixed wing for speed, you lose takeoff and landing capability. If you design it for takeoff, you lose speed. The variable wing resolves this contradiction. But building a moving wing on a supersonic heavy bomber isn't like putting hinges on a door. What's done? A central structural pivot, the most heavily loaded part of the entire aircraft, is built, capable of withstanding the forces generated by a wing of that size moving at high speed. The sweeping mechanism uses high-pressure hydraulic actuators. The wing can move between 15 and 67.5 degrees of sweep while the aircraft is in flight. What do you get? A bomber that takes off with the necessary ease to operate from standard runways and that seconds later can fly like a supersonic fighter at low altitude. What advantage does that provide? Operational flexibility that no fixed-wing aircraft can replicate. The B-1B can operate from bases that a conventional delta-wing bomber couldn't use. The next part of the process will help you understand why this aircraft sounds unlike anything else in the sky.
We are approaching 90% of the maximum load. Check the trailing edge deflection.
Deflection is within tolerance, sustaining current pressure.
Load is approaching 90%. Check the trailing edge displacement.
Reading stable at 4.2 inches. Strain gauges holding nominal.
Here we see the slat extended in low-speed configuration. The precise gap creates the control.
Alignment is within tolerance. Confirmed on the laser tracker, Charlie. Green across the board.
Proceed with final fastening sequence. Check the starboard side readings again.
Confirmed. Alignment is perfect.
Proceed with the automated fastening sequence.
Sweep is smooth.
Acknowledged. Time and smoothness are within tolerance.
Four engines, General Electric F-101-GE-102. With afterburner, each one generates more than 30,000 pounds of thrust with afterburner active, 4 times that, in an aircraft that already has a brutal thrust-to-weight ratio for its size. What happens in this phase? The engines are integrated in pairs under the wings, 2 nacelles with 2 engines each. The integration includes the fuel supply systems, air intake ducts, and afterburner control systems. Why 4 and not 2 like many bombers? Because the B-1B needs that thrust for what it does. Fly very fast, very low, where the air is dense and aerodynamic drag is multiplied. 2 engines wouldn't provide the acceleration necessary for air defense penetration maneuvers. What is achieved? A bomber weighing more than 200 tons at maximum takeoff weight that can accelerate and maneuver like a much smaller platform. What advantage does this offer? The B-1B can do something few people know. In close air support missions, it can reach a target from 1,000 kilometers away in less time than it takes to organize a fighter escort. It arrives alone, fast, with 34 tons of weaponry. But the engines are only part of the problem. The part that almost destroyed the entire program is what comes next.
Easy, easy. Bring the rear mount down 50 thousandths. Copy that, coming down slow. Looks aligned now. Easy, lower slowly now.
Watch the clearance on the left.
Hold it steady, we have alignment.
Setting the first bolt.
The vibration levels are spiking on engine 4.
I see it. Keep monitoring the EGT.
When you arrive at the final assembly of the B-1B, you're witnessing something few assembly lines in the world can do. The separately manufactured fuselage sections, nose, center section, rear section, are joined together with tolerances of tenths of a millimeter into a single airframe nearly 45 meters long. The wings, with their entire variable sweep mechanism, are integrated into the center section. The 4 engines are mounted in their nacelles under the wings. The landing gear, which must withstand landings with more than 200 tons, is installed and tested. The 3 internal bomb bays are completed and integrated with the weapons management systems. What happens here? The fusion of everything: fuselage, wings, propulsion, avionics, weapons, flight systems. Every subsystem has to communicate with the next. Every cable, every actuator, every sensor has to be exactly where it needs to be. Why is this moment so critical? Because a bomber is not simply the sum of its parts. It's the integration of its parts. A perfect engine in a poorly integrated fuselage is a plane that doesn't work. What do you get? A machine that at first glance seems impossible, enormous, heavy, loaded to its structural limits, and capable of flying at Mach 1.2 at low altitude. The ultimate advantage is this: when the B-1B rolls off the assembly line, there's no other bomber in the world that can carry what it carries, so fast, so far. Now we have to prove it flies.
Flap control system check. Verify engagement at position 5.
Affirmative. Cycling flaps now. Indicators show green.
Confirmed. Checklist item complete.
Initiating gear swing sequence now.
Roger that. Monitoring hydraulics pressure on GSE.
Pressure steady. Cycling green.
We have a failure on the data bus integrity check. I'm running the secondary diagnostic through the specialized test set now.
The alignment is holding steady at 99.8.
Confirmed. Drift rate is nominal.
We have a slight fluctuation on the pitch axis here.
Let's cross-reference with the manual. It seems within tolerance.
Did you see that spike on the navigation strobe? Yeah, the bus reconfigured automatically. Test sequence is proceeding nominally.
Here's the part that almost no one mentions when talking about the B-1B. When the first aircraft rolled off the assembly line in 1986, they had a huge problem. The electronic warfare systems, the ALQ-161, were a disaster. They didn't work well. They were unreliable. And without those systems, the B-1B can't survive in a modern air defense environment. In its first year of operation, fleet availability was so low that the aircraft was publicly ridiculed. A state-of-the-art supersonic bomber that couldn't fly regular real-world missions because its own internal systems kept failing. What happens in this industrial phase? Integration of avionics racks within the airframe, connection of sensors, inertial navigation systems, terrain-following radar for low-altitude flight, and the entire electronic warfare system. Why is it so difficult? Because the number of systems that have to communicate with each other in real time is enormous. And in the 1980s, mission software integration was much more complex and less reliable than it is today. What is achieved when this problem is solved? A bomber that can fly 60 meters above the ground in total darkness, automatically follow the terrain, evade radar, and simultaneously launch precision weapons. What advantage does subsequent modernization provide? That the same aircraft that was problematic in 1986 can now launch JASSM-ER cruise missiles with a range of over 900 kilometers from distances that keep it completely out of reach of enemy air defenses. An industrial failure that became a platform far more capable than it originally promised.
Systems check, page 12, verify pressure nominal.
Confirmed, SO2 station.
Copy that. Proceeding to engine start checklist. Engine 1 and 2 stable. Roger. Roger. 3 and 4 spooling up now. All engines idle and stable.
Testing the B-1B isn't like testing a conventional airplane. The wing sweep tests are done in flight. The aircraft has to demonstrate that it can move those wings from 15 to 67 degrees while flying, under load, without anything failing. If the mechanism fails in flight with the wings extended, the aircraft can't go fast. If it fails with the wings folded, the aircraft can't land properly. The low-altitude flight tests are the most critical. The B-1B has to demonstrate that it can fly 60 meters above the ground, automatically following the terrain. 60 meters, at high speed, in the dark. That's the terrain-following system, working under real-world conditions. The weapons load tests verify that all 3 bomb bays function, that the weapons management system releases correctly, and that the aircraft doesn't lose control when it releases several tons of weaponry in seconds. What does all this achieve? Certification that a machine manufactured piece by piece on an assembly line can do in the real world what the engineers promised on paper years before. And the advantage? Simple. Every hour of testing yields data. And that data is what has been improving a platform for decades that today, 40 years after its first flight, remains one of the most feared in the American arsenal.
Look at the altitude trace here at T+40. That spike is outside the envelope.
Yeah, I see it. Cross-reference with the engine parameters.
We're seeing a consistent deviation in the flap position data.
Is that reflected in the angle of attack measurements as well?
And this is how the B-1B is built. If you liked it, give it a like and subscribe. This is Global Arms Factory.